Hello, everyone, and welcome to the live stream for today, April 3rd, 2025. My name is Matthew. I am one of the course staff for our online classes, and I do a lot of behind the scenes things here on our channel. And I just want to say thank you for joining us today. We are excited to be here. There's all sorts of good astronomy news and content that we can discuss, and we always have a great time answering your questions. Let me do a quick overview of how this works. Please post your questions in the chat. I will go through and moderate those questions. We try to pick questions that are at a beginner level. This is kind of an introductory level discussion. We will try to go through a variety of topics and give everybody a chance to ask questions. So I try to generally go in order, but jump around. Please ask your question only once. I know that sometimes it feels like we aren't getting to it, but either it was at a high level or just is in the queue, and we will get to it. I think that's it. Chris, why don't you welcome everybody? Say hello, and you can get this started with kind of a topic for discussion.
Sure. Welcome everyone to our live session for the online classes, or however you found us. I thought I'd start today with a story that came out a couple of weeks ago and has spurred some interest. It's about an object called Kipu, Q-U-I-P-U, and it's claimed to be the largest structure in the universe. It's quite a strong claim, so I should unpack it a little and say what it's based on. The large structures in the universe are larger than galaxies, of course. They're larger than clusters of galaxies. They're essentially superclusters of galaxies. And this object was found by X-ray astronomers. And so you might wonder, what have X-rays got to do with finding and counting galaxies? And the answer is that rich clusters of galaxies, the biggest concentrations of matter in the universe that are in a compact form, have very hot gas in their cores, X-ray emitting gas with millions of degrees. And that just stands out to radio telescope. So X-ray surveys are very good at picking rich clusters of galaxies and doing surveys. So these X-ray astronomers, put together all the X-ray surveys, identified all the rich clusters, and then they used a sort of clustering analysis, a friends of friends, friends of neighbors analysis, to look for coherent structures that were much larger than the individual clusters. So there are clusters of clusters. They found 4 or 5 structures, each of which was enormous, of order 1 billion light years across. And Kipu was about 1.3 billion light years across, which makes it the largest. It's these are not spherical. The rich clusters themselves are spherical. And they're collapsed objects held together by gravity. When you get to superclusters, it's a little trickier, because in the theory of the universe of top-down structure formation, the small things form first and aggregate to form larger things. And something as large as hundreds of millions of light years across is really only just forming, and so it's not going to be a spherical structure. And it's even argumentative whether it's a gravitationally coherent structure held together by its own gravity. So you're using a statistical analysis to identify it. And they did. And this object is really impressive, of course. It's elongated. It's one long filament with several side filaments. And it contains an extraordinary amount of mass. If you add up all the galaxies, it's 200,000 trillion solar masses of stars in this supercluster. Kipu is an Incan word from their way of counting using knots on rope, which is kind of appropriate, since the knots are like the rich clusters of galaxies, and the ropes are the filaments that connect them in the universe. So this is an interesting story, and I'm sure there will be claims of larger structures still to come, because this object was only half a billion light years from the Earth. That's fairly close, and as people look at larger and larger volumes, it's quite possible there are even larger structures.
Excellent. Thank you very much for that overview. I'm sure that will trigger some questions in our participants. One thing we're noticing is there's a little bit of a hum or a buzz on the line. I don't know if you can stretch the audio cable out a little bit more. Sometimes
Oh,
I
yeah.
know that has a little bit of effect on it.
Okay.
All right. Excuse me. The first question for today is from Monty Roeder, who asks, with the new ELT and Galileo project, do you think we'll find beyond a reasonable doubt evidence of life in the universe within the next 10 years?
I think the general answer to the question is a good probably yes. Whether it comes from the ELT or from our own Giant Magellan Telescope or the possible Caltech California TMT, 30-meter telescope, those are the three big telescopes that each can do this experiment. It's not clear, but ELT, indeed, the European project is going to be first to the game because they're under construction, they have all the funds they need, they have their site, and they have instruments developed. So the experiment, of course, is looking at Earth-like planets, sniffing with spectroscopy the atmosphere of those Earth-like planets and looking for biomarkers, looking for the signatures of biology, which on the Earth would be oxygen, of course, ozone, methane, and water vapor, because you need water to have life. So this experiment is compelling and it's challenging because Earth-like planets are hundreds of millions to a billion times fainter than the star they orbit, which is very close to it on the sky. So you need adaptive optics, exquisite suppression of the central star, and high degree of stability in your spectroscopy to detect these faint species of chemicals, all of which is not insurmountable. And so I agree that this experiment will be done in the next 10 years. Whether it finds life or whether the first 6 or 10 examples that are looked at turn out to not show biomarkers will be very interesting and will indicate in some large degree whether microbial life is abundant in the universe or not.
The next question is related, and you've answered some of it, but we'll talk a little bit about the second half of it. So a new study says the ELT should be powerful enough to detect signs of life on nearby exoplanets in just a few hours. You've talked a little bit about how that's possible. What sort of big biosignatures will it be capable of detecting?
So the spectroscopy is mostly done in the optical regime. It can also extend into the near infrared, which is useful because the contrast of the planet is cool and the star is hotter, and so the planet is relatively brighter compared to the star than at optical wavelengths. It's still fainter by many orders of magnitude. So near infrared is also a way to do this experiment. If you go into the near infrared, you can look for other species. So essentially you're asking what are the gases that are generated by biology. And on the Earth, after photosynthesis was invented by biology, oxygen became a biomarker. But before that, there were methanogens, and so methane is a biomarker. And really those two stand out as the prime biomarkers, where if they have high degree of abundance in an atmosphere, it almost certainly does not have a simple geological cause and must have a biological cause.
Excellent, thank you. The next question is from Wendy Traver, who sent an email. Can a moon or exomoon be more massive than a planet?
There is an overlap in the range of masses of moons and planets. That's true in our solar system, and we expect it to be true elsewhere. In the sense that the moons of the giant planets in our solar system, the biggest of those moons, moons like Titan and Enceladus, not Enceladus, but Europa and the Galilean moons of Jupiter, these rival the planets, certainly dwarf planets like Pluto. And elsewhere, we could expect there to be examples of exomoons that are actually larger than some of the planets in their system. So there's no hard and fast rule. It's not a rule that a moon has to be smaller than all planets in a system. Most moons, however, will be. Jupiter and Saturn in our solar system have literally hundreds of moons, and most of them are really small, like 5, 10, 50 miles across.
And kind of a related question, one of our participants would like to know, is it possible for a moon to have a moon? Can you have a moon?
Yes, there have been a few amusing and interesting articles written about this. It is indeed possible for a moon to have a moon, because the same process that forms a moon could lead to a debris disk around it that coalesces into a little moonlet. I guess that's the word you would use for it. We don't know if that actually happens, and we certainly don't have a way of detecting it beyond the solar system. But yes, in principle, moons can have moons.
The next question is from Adrian Murray. I hope I'm interpreting this question properly. But the question is, the question is, what is the extent of the event horizon of the James Webb Telescope? And based on the second piece of this, what percent of the universe may be beyond the visibility of the James Webb? So I think they mean what percentage of the universe is outside of the visibility, has passed beyond our ability to see it, or is too far away, that we can't observe it.
Right. So there are different types of horizons in astronomy, and it's important not to confuse the event horizon of a black hole, which is a very particular thing associated with the black hole distance from which nothing can escape, including light, and that's a very small distance, from a cosmic horizon. The cosmic horizon is essentially the boundary where light cannot have reached us, given the expansion of the universe, in the age of the universe. And because the universe has had an accelerating expansion, it's essentially certain, if our cosmology is correct, that there are regions outside our horizon. In other words, regions that we cannot see with current telescopes and that we will not ever see, actually, given the accelerating expansion. And this is not particular to James Webb. Any telescope is subject to this, because this is not a limitation of the telescope and its optics or the size of its mirror or its instruments. It's a limitation imposed by the expansion of the universe, essentially.
The next question is from Jobin, who would like to know, and they ask it one way, but I'll kind of ask it both ways. They ask, is there a reason to consider the universe an isolated system? And I guess the reverse is, would we have any reason not to consider the universe an isolated system?
The universe, the word universe essentially means everything there is, mass and energy and everything there is and everything we can see. So we tend to think of the universe in general as a monolithic thing. It is all of space and time available to us or visible to us. Whether that's all the space and time, as mentioned in the last question, the accelerating expansion of the universe means there's regions of our universe that we cannot see, even though we know they are going to exist beyond our horizon. But that's not the same as saying there's another universe. The idea of other universes, in the plural, is the multiverse idea, and that's really rooted in quantum cosmology and the idea that the universe formed as a quantum entity, and perhaps there were other quantum entities 13.8 billion years ago that expanded to form their own universes. Completely hypothetical and speculative, so there is essentially zero evidence for other universes right now. We're kind of just stuck with the one we have.
Excellent, thank you very much. The next question is from one of our live participants. Professor Impey, how do we know Pluto's rotational speed, diameter, and revolution? And was it once believed that these measurements were drastically different during the 1930s after it was first discovered?
So now we know Pluto's rotation period and its orbit extremely well, because we've got much larger telescopes than were around a century ago when Pluto was discovered. And we can essentially, and we've had a spacecraft, we've had New Horizons visit Pluto. So there is good enough data on Pluto to map out its orbit and its rotation. That's been measured for several decades. That was not possible soon after Pluto was discovered, because Pluto was discovered by Clyde Tombaugh in 1930, and it was using a small telescope, a less than 2-meter telescope at Flagstaff and Lowell Observatory. And with that kind of a telescope, even on a good site, you can't resolve enough of Pluto and its features to track it over time and say what its rotation is. So it took a different generation of telescopes to be able to make those observations.
Excellent, thank you. The next question is from Richard, who's on with us live and asks, if dark matter is such a large part of the mass of the universe, how can some galaxies not appear to have any dark matter based on their rotation rate?
I think that's controversial contention, that there are galaxies without dark matter. Every now and then there is a paper that proposes that they found a galaxy without dark matter. Most of them turn out to be wrong or just misinterpreting the data. We think galaxies form within dark matter halos that account for 75 to 80% of their mass. And then the visible matter nucleates within it and then condenses, collapses by gravity, and forms stars. And that's how we see the galaxy. So it's just essentially a part of galaxy formation theory, which is a good, robust, and mature theory, that all galaxies will have dark matter. The way you can possibly have a galaxy without dark matter is to have a situation where galaxies interact or have a collision, and somehow the stellar component gets separated from the dark matter and then sails on through intergalactic space. And then if we subsequently observe it, we'll see this stellar material without any surrounding dark matter. So it's really only due to complex interaction or collision of galaxies that you could seem to have any galaxy without dark matter. Otherwise, with good measurements, galaxies all seem to have dark matter.
Thank you. The next question is from David Gold, who asks, is philosopher Immanuel Kant's nebular hypothesis from 1755 still recognized excuse me, in the field of astronomy today, or has it been superseded by other theories?
Well, Immanuel Kant, who is a philosopher, of course, by training and made important contributions to philosophy, but he thought deeply about astronomy and he talked to astronomers and he was aware of the observations that had been made with the telescopes of his time. So he was clearly far ahead of his time because he was essentially the first person to propose that some of the fuzzy nebulae that were being cataloged by Messier and Herschel were island universes, to use the phrase, that is, separate distances, systems of stars beyond the Milky Way. So he was definitely way ahead of his time. He was 150 years ahead of his time in the sense that that's how long it took Hubble to prove that hypothesis. It was a pure hypothesis, but from a theorist and a philosopher, he had no evidence to back it up. But it's intriguing, and yes, he does and should get credit as the first person to speculate about galaxies as external stellar systems.
The next question is again from one of our live participants. Knight Ventura would like to know, what are the factors that make a multiple star system exist instead of just a single star?
A multiple star system is the most common circumstance. Stars do not form singly, essentially. Stars usually form in dense regions of molecular clouds or molecular gas that's cold and then collapses. And the mass of a molecular cloud can be thousands or tens or hundreds of thousands of times the mass of the sun. So the large clouds of gas that form stars are able to form many stars at one time, and that's what we think happens. The Orion Nebula is a really good example of that, because in the Orion Nebula we see young stars forming right now, and the mass of the nebula is clearly sufficient to form hundreds of stars. Now, why? So stars will tend to form in multiple systems, and therefore it's not surprising that less than half of all stars are single stars like the sun. The sun is slightly unusual. Most stars are in binary or multiple systems. And they go up to large multiplicities, 7, 8, 9, 10 stars. Over time, even though stars form in large aggregations or clusters, they will disperse. They will get random velocities that disperse them or make them move away from their place of origin. And so the things that's happening in Orion right now, if you look at it in 10 or 100 million years from now, those newly formed stars will move away from their origin place. They may still be in binary or multiple systems, but there will be no large aggregation of stars.
The next question is from Rose Cynthia, or Cynthia Rose, who's on with us live and asks, after the second stage of the Saturn V rocket was cut off, what happened to it? I've heard that there are stages of the Saturn V that are still orbiting, that disappeared off into space. I know some pieces landed in the ocean. Which one of these is true?
Mostly they came to Earth. I think almost exclusively they came to Earth. The second stage was what took the Apollo, second stage of the Saturn V rocket was what took the Apollo probes to Earth orbit, and then they were jettisoned when the fuel was gone. Now in low Earth orbit there is drag caused by the very thin atmosphere of that elevation, and so an object like a jettisoned booster rocket will not stay in that orbit forever. It'll experience slow drag and will tend to fall to the Earth. So essentially, for very high probability, all the Saturn V second stages fell into the ocean. Some fell into the ocean soon after the launch, and so we know they fell into the ocean, but any that may have been left in Earth orbit would now, half a century later, have fallen to Earth or in the ocean too.
The next question is from Christina V, who sent a question via email. Could there have been a hot Jupiter in the early solar system that was eventually swallowed by the sun?
That's an interesting question and a hypothetical, and the answer, I guess, is yes, because we don't really know the initial conditions of the solar system, and there was a large-scale rearrangement of the orbits of the planets. We know the giant planets that we have now, the 4 giant planets, changed their, 2 of them swapped positions, and they changed their distance from the sun quite significantly. So it's entirely possible that there was yet another giant planet early on that experienced drag or perhaps interacted with one of the other planets, which kicked it in towards the sun, and it would have fallen into the sun. Remember that even a Jupiter is 0.1% of the sun's mass, so it doesn't add much to the sun's mass to swallow a Jupiter whole. So it's entirely possible there was a hot Jupiter forming early in the solar system that quickly vanished as it fell into the sun.
Excuse me, next question is from Remis Guide, who asks, Professor, do you think we can form a theoretical link between the Penrose process equation, where black holes lose angular momentum, and Hawking radiation? Do you think that there is a connection there?
There could be, and Penrose and Hawking work together extensively, actually. Hawking and Penrose wrote a very dense gravitational book on general relativity, and they came up with a set of singularity theorems applying to black holes. So they did independent work on black holes and combined or joint work on black holes. The Hawking mechanism of radiation doesn't require anything else. It's this completely self-contained idea. And so you don't actually need to put the Penrose hypothesis on the table to explain Hawking radiation.
The next question is kind of a follow-up related question to hot Jupiters. Can a hot Jupiter eventually turn into a rocky planet if its atmosphere, or after its atmosphere, is stripped away or off by a star?
In principle, because the Jupiters that form, whether they're hot or cold, do have rocky cores, we suspect, and have good reason to believe from simulations that all giant planets have rocky cores that are 3 to 10 times the Earth's mass. So if a hot Jupiter is close enough to its star for the stellar radiation to ablate or blow off the atmosphere, then what you're left with is a small rocky core. But that rocky core will also experience drag in the outer part of the stellar atmosphere and will, of course, suffer frictional drag and will be falling into the star. So even if the rocky core survives the ablation of the giant hot Jupiter's atmosphere, the rocky core will eventually be swallowed by the star.
Excellent, thank you very much. The next question is from one of our live participants. Let's see. So P51 asks, have you heard something, or I've heard something about a new planet found around Wolf 327. Can you talk about that planet, that planet and star specifically, or can you just talk a little bit about how quickly we're finding exoplanets and how many are currently that we know about, and
Sure.
how fast are they coming in?
That particular planet, there's exoplanet discovery occurs at a rate where I can't keep up, so I don't know about individual exoplanets, unless they're very special or unique or distinct, and then they get more publicity. The rate of exoplanet discovery has cooled slightly, I would say. The peak of the growth of the number of exoplanets came during the Kepler mission, NASA's Kepler mission. And that essentially led to a doubling of the number of exoplanets in just a couple of years, 3 or 4 years. The pace is slowed as people do their work with not the same kind of discovery tool that NASA had provided. The current number sits just a bit under 6,000 confirmed exoplanets on NASA's website. Maybe it's about 5,850 at the moment. And that number is probably going to be going up by a dozen a week. I mean, so it's a pretty rapid rate of growth. But people are really pivoting a little bit beyond discovering yet more to understanding the ones we already have. In particular, the idea of characterizing the habitable planets, the so-called habitable planets, the ones that are Earth-like and within the region of their star where liquid water could exist. That's the prime directive now of exoplanet research. And so there are still surveys, there are still people trying to find more exoplanets, but there's probably more the research groups are homing in on understanding the most Earth-like of the exoplanets we already know about, which is several hundred.
The next question is from Hernan Reyes, who is, I think, on with us live, but sent an email. There's kind of 2 parts, but the first part of the question is that he read an article recently on space.com which said that small planets are common and large planets are rare, and that large planets need metal-rich stars in order to form, whereas small planets do not. Can you talk a little bit about whether that is accurate or how that might work?
I think one part of that contention is more secure than the other. The fact that there are more small planets than large planets, that's clearly demonstrated. It took a while to know this because, of course, it's harder to detect the Earth-like planets or the super-Earths than it is to detect the Neptunes or the Jupiters. But now there are enough surveys that have been done that we can correct for the sort of selection effect that makes it easier to find big things than small things. And so it is a fairly secure statement now that small planets dominate, to the level where essentially every star in the Milky Way has at least one or more Earth-like planet, and probably fewer gas giants. The business of the metal-rich or the heavy element abundance of the star is a little confusing. There's not been a lot of pivotal research on this, even in recent articles. The contention is that you need heavy elements in a forming star region to create a stellar core, to create a rocky core, to make an Earth-like planet, or the rocky cores in the giant planets. So there is a correlation. There's always been a correlation between the heavy element abundance of a star and the likelihood that it will have exoplanets. Because if it's a star that formed out of a cloud that had few heavy elements, then there's not many heavy elements there to make planets. So that trend and correlation was first found about a decade ago, and it hasn't really changed. Remember that it's all based on what happened before, so it's really based on what was present before the star formed. So it's not the fact that the star itself is forming heavy elements, as the sun is doing with hydrogen to helium, and more massive stars are forming heavy elements. Those elements don't play into the planets because they're trapped inside the star until it ends its life. So it's really what the pre-existing heavy element abundance was in the cloud that formed the star and then the planets.
Excellent, thank you very much. The next question is from one of our live participants. Laura would like to know, excuse me. She says, I admire your work very much. While studying astrobiology and contemplating the vastness of life beyond Earth, have you ever experienced something akin to the overview effect? And has it influenced your perspective on humanity or your work?
It's an interesting question. I haven't experienced the classic overview effect. The classic overview effect is that that many, but not all, some fraction of astronauts report that when they go for the first time into Earth orbit on the space station, for example, and they see the Earth as a seamless planet where it's just impossible to see. You can see the lights at night, of course, but you can't see any individual structures. You can't even make out the Great Wall of China or the pyramids. So our constructions are not that impressive, and the boundaries are invisible, of course, between the countries. It's a seamless planet. And for many people, many astronauts, that's a profound awareness, just making us realize that we're on one planet. And also they see the fragility of the atmosphere, because as seen from the International Space Station, you can just clearly see how thin the atmosphere is before you get to the blackness of space. So no, I would love to experience Earth orbit and have a true version of the overview effect. I'd say probably the closest I've ever come is by being in, very high altitude, remote environments where I can see hundreds of miles and get a sense of the vastness of the planet that we live on and spend most of our times in little parts of. And I guess the two places I've witnessed or experienced that were in Chile, in the northern part of Chile, on the edge of the Andes, where you can see across the Atacama Desert and the plain and all the way across to the ocean in Chile. So it's easy to see 100 or 150 miles and get a sense of the vastness of South America. And I've had a similar awareness in Asia, visiting Everest Base Camp, for example, or in places in Nepal where from a high elevation, 4,000 meters, 5,000 meters perhaps, you again can see an enormous distance and range after range of mountains, getting a sense of the vastness of this planet.
The next question is from one of our live participants who would like to know, I recently came across the concept of zero-point energy, and I would like to know how much research has been done on this topic in the scientific community.
Zero-point energy is a concept that goes back to the foundation of quantum theory, so 100 years ago. When you actually look at when you work the quantum theory for what the energy states of atom or even of the vacuum are, there is a irreducible zero-point energy, and it's essentially h bar divided by 2 pi, so h bar being the Planck constant. And so there's a small amount of energy at the level of a quantum of energy that exists even in the vacuum of space. So space is not truly empty, it has a vacuum energy. And the proof of that vacuum energy is in physics experiments like the Casimir effect experiment done over half a century ago, where you can see that vacuum energy exists because it acts to exert a force on two plates in their electrostatic repulsion. So you can manifest the vacuum energy, so we know that it exists, and we've known that for a long time. But again, it's all at an incredibly low level, so this is not visible or present in the everyday world or even in the normal lab situation, because a quantum of energy and the Planck constant is an incredibly tiny number.
The next question is from one of our live participants, Lawrence K. would like to know, what is the latest on dark energy? There are other people also asking what is dark energy. So can you just talk a little bit about the current ideas about dark energy? Has the current theory of dark energy been thrown into doubt? What is the latest on our knowledge of dark energy?
Yeah, I mean, the update is we still don't know what it is. So the 0th order answer to the question is we don't know what dark energy is. There are many ideas, dozens of ideas, dozens of theories. And we're limited by observation because it's a very hard thing to measure. It was found, of course, by noticing the accelerating expansion of the universe. And since then, and more recently, it's been diagnosed by large galaxy surveys, which can map out both dark matter and dark energy on very large scales. So in the news recently, very recently, has been the Dark Energy Survey, DES as it's abbreviated, that's been conducted at the Big 4-meter telescope, which was turned from a general purpose telescope and given a new life as a survey telescope. And it's been mapping out a large swath of the sky to very faint levels and counting galaxies and looking for the effects of dark energy. And it has a tentative result, not confirmed, and probably at a statistical significance level that won't convince everyone, that dark energy is not constant over time, but has actually been varying over cosmic time. That would be a very profound discovery. Now, dark energy does not seem to vary in direction in the sky, so it's isotropic in that sense. But if dark energy changes its strength over cosmic time, then that means it is not the cosmological constant proposed or calculated by Einstein when he developed his general theory of relativity. It means something more interesting is going on. Now, having dark energy vary over cosmic time is a clue to its fundamental nature, but even with that observation, if true, there are dozens of theories to explain why dark energy might vary. So theorists are having fun with this, but the observers are being cautious because they want to be sure this is a real result. Because if it varies with time, it will be the first fundamentally new information about dark energy in 10 or 15 years.
The next question is from Jake Johnson. The question is the scientific consensus or is it still the scientific consensus that the moon was formed when a large bolide struck the Earth? But more generally, can you just talk about what we know about the moon's formation?
Yeah, it's still a consensus, and there has been recent research that addresses this. The idea of the moon forming from an impact on the infant Earth by a Mars-sized object has been around for decades, and it is bolstered by simulations which show how that impact could have happened and give the moon its properties, which is a very large satellite compared to the Earth. That's unusual. It's anomalous in the solar system. And then more importantly, we have the geology of the moon rocks, which bolsters the fact that the moon is made primarily of Earth mantle material, which is what would have been thrown off in an impact. And the moon, of course, doesn't therefore have a large metallic core that the Earth does. If it had formed independently, we might expect to see that. The recent data has tried to narrow down the timing of this event. So for a while, it was thought that the moon formation was maybe as much as 100 million years after the Earth formation. But recent data suggests it happened very quickly, very soon, maybe 30 million or less years after the Earth formed. And that's new information. It's also based on geological data from moon rocks and simulations. So we're learning more about the nature of that impact, and that's actually helpful that the moon formed that soon after the Earth formed, because it explains, it reduces what was a small discrepancy between the age of the oldest moon rocks and the supposed age of the solar system.
The next question is from Bina M, who sent an email. I have a question about the moon illusion. I have not ever heard or read a satisfactory explanation for why we see the moon as being so huge when it's near the horizon. Initially, I thought maybe it was similar to an optical illusion or mirage, but I don't think that I've read any convincing explanation. Do you have an explanation, or do you have an opinion on it?
Well, there are two things that could be happening when the moon is near the horizon. One is that you actually can get atmospheric refraction effects, and those refraction effects, depending on how the density of the lower atmosphere changes with elevation, could actually magnify the apparent size of the moon slightly. Not a big effect, but it's a real effect. That's one thing. And then the other one is a psychological one, and that's the thing people argue about, because optical illusions and psychological illusions are not locked in stone. They do sometimes depend on the perception of the viewer. So the idea is that when the moon, high in the sky, the moon you have no other reference for the moon and its apparent size. It's just floating in space with nothing nearby as a reference for angular size. When the moon is near the horizon, then you have other references. You have the references of a silhouette of mountain ranges or possibly buildings even in a city. And that adjacency, in a psychological sense, tends to slightly elevate the impression of the moon's size relative to being higher above the horizon. And people have done experiments, of course, on this and tried to test this idea. And the data is not completely convincing, which is why people still argue about it.
The next question is from Manjot, who is on with us live. How much or how often are intermediate black holes studied in astronomical research?
Intermediate-sized black holes are very important because filling in the gap in the black hole mass spectrum is important. We know that nature can essentially make black holes of any mass, down to 3 solar masses for a dead star. A 10 solar mass star will die and make the minimum the minimum collapsed star black hole about 3.5 times the mass of the sun. And we know that the biggest black holes in giant galaxies go up to 60, 70, 80 billion times the mass of the sun. And then there are smaller black holes like the Milky Way one. It's about 4 million times the mass of the sun. The intermediate black holes tend to be found in globular clusters and smaller stellar systems of the scale where you would expect the black hole to be smaller, or at the centers of small dwarf galaxies. So when people talk about intermediate black holes, they're talking about a range between about 10,000 times the mass of the sun and 1,000,000 times the mass of the sun, somewhat smaller than the Milky Way black hole. And there's only really been a small number found, and for a long time it was just a handful, and now I think it's still only a dozen or so. They're very hard to find because, again, they're small mass black holes and they're not in the nearest galaxies necessarily, so it's actually hard work to find them. But so far, there's evidence that nature will make every black hole mass in between a few solar masses and billions of solar masses.
Excellent, thank you. The next question is from Arif Roni, who says, I recently learned that you were the past vice president of the American Astronomical Society, which is a 125-year-old science community. Can you tell us about the AAS VP experience?
Sure. American Astronomical Society is our professional organization and has been around for over a century. And its primary function is providing a place where, especially through the 2 meetings it holds, biannual meetings, or one in January and one in June. And the ones in January tend to be bigger because they're associated with job fairs, and they tend to be in large East Coast cities, and the summer meetings tend to be scattered more around the country and are smaller because people are doing other things during the summer. So the AAS hosts meetings. I think the membership of the AAS is something like 7,000 or 8,000. At the biggest meetings, maybe half that number will actually go, when the meetings in Washington, D.C., for example. So the meetings are a big function of the AAS, but it's also got a council that deals with governance issues of professional astronomy, that tries to do some advocacy over funding for astronomy. They have an education board that deals with education issues. They have a publication board that deals with the professional publications or journals that astronomers tend to publish all their papers in. So there's a lot of activity. The primary function, actually, of the vice presidents, of which there are 3 at any given time on sort of overlapping 3-year terms, is to organize the meetings. And so when I was vice president, I was on the council, of course, so I got to hear all the discussions about the high-level stuff we were dealing with. But the roll your sleeves up work of a vice president was planning the meetings, and that means organizing the sessions, deciding what special sessions were needed, inviting the keynote or plenary speakers, so the high-profile speakers that open sessions or open the entire meeting, deciding how many breakout rooms are needed, what kind of workshops there should be. I mean, there's help for that from staff. But planning the meetings is substantial work, and it was enjoyable. It was good to learn how the mechanics of a meeting work, and of course there's very professional staff that actually run the meeting, so the vice president's work is done once the meeting is in the books and all planned and the abstracts have been published, then everyone just gets to enjoy it.
The next question is from one of our live participants. Abhinav's Astronomy asks, what evidence or proof do we have that the universe is expanding?
Very good evidence, of course. This expansion of the universe was first measured in 1929 by Edwin Hubble, so almost 100 years old now, and there'll be big celebrations of that centenary, I'm sure. We just had celebrations of Hubble's demonstration that galaxies are external stellar systems. And so back then the evidence was slender. There were only a few dozen galaxies in Hubble's first graph of cosmic expansion, and they were at relatively small distances, tens of millions of light years. Since then, thousands, tens of thousands of galaxies have been observed, their redshifts, their distances calculated, and so we can plot the graph that Hubble did and populate it with literally thousands of galaxies. So the Hubble expansion, the expansion of the universe, the linear relationship between the redshift or recession velocity of a galaxy and its distance from the Milky Way, is a sort of ironclad foundational principle of modern astrophysics. And it indicates that the universe is evolving, and it indicates not only that it's expanding, but if you trace time backwards and run the clock backwards, it shows that the universe was once much smaller, hotter, and denser. And the origin we call the Big Bang.
The next question is from Andy, who's on with us live. Besides your impressive scientific work, you've educated a large number of people in astronomy. Do you find your educational mission more valuable, and what's your personal goal in teaching?
Yes, I like teaching a lot. I'm teaching right now, teaching an upper division course on the history and philosophy of astronomy to a nice small group, about 15 students. Most university faculty, not just in astronomy, but in all subjects, have a multiple mission. Their mission is doing research or scholarship. Their mission is teaching, and they have a service mission. So they're supposed to help their department, their university, or their profession by doing service work. And in my case, and in the people in my department, and this is also common elsewhere, the breakdown of that is typically 40% for research, 40% for teaching, 20% for service. So that sort of describes how your work week is apportioned. I do enjoy teaching. I teach as much as I can. I also like to travel, and travel sometimes makes teaching harder. I'm in a very research-intensive department, and so my teaching load, I think many faculty colleagues at other universities would say is enviably low, because they often have to teach multiple courses each semester, and I don't have to do that. On the other hand, the expectation for research at a Research One university is very high. And so you are expected to produce, you're expected to get grants, you're expected to write papers, you're expected to move the bar on knowledge, and so the teaching sort of takes care of itself in a sense. So that's why research sometimes gets more attention than teaching at research universities.
The next question is from Laura, who's on with us live, who asks, what are your expectations for NASA's Europa Clipper mission and the potential Europa lander? Do you think we might find strong evidence of habitability or even biosignatures?
So the Europa Clipper mission is an exciting mission. It's on its way. It's a long trip, so we shouldn't hold our breath. And it's not a mission that is really going to detect life. I mean, people get excited about Europa as a possible place with biology in the ocean under that ice pack. But this mission, the Europa Clipper, does not have a lander. It does not have anything that will do direct life detection. The primary mission is an orbiter. There's a component of the mission that will have the capability of sending a projectile to the surface to splash off ice material and then sniff it spectroscopically, which could detect life-bearing molecules. That would be very exciting. That's as close as Europa Clipper will come to life detection. The idea of a lander was weighed up, and the mission was being planned, but it was going to add so much cost and complexity to the Europa Clipper that they decided not to do that. So unfortunately, it's going to take a second subsequent mission to land on the European surface and, say, drill down through the ice, or potentially drill down deep enough where the ice is thin to release a little hydrobot or some life-sensing probe. That would be another exciting step in understanding Europa, but that's several decades away.
The next question is from Sharvan Kumar, who asks, is it possible that we could use asteroids or some other orbiting body as sort of a space taxi to deploy our observational devices instead of using costly spacecraft like Cassini, so that we could observe things extremely far away, like out towards the Oort cloud?
The idea of using asteroids, or co-opting an asteroid as a space platform or a telescope platform, it's intriguing. but the requirements are quite strict. You'd have to have an Earth-crossing asteroid, so not one that just stays out in the asteroid belt a billion miles or more from the Earth. You'd need an asteroid on a highly elongated orbit that took it close to the Earth, and you'd somehow have to fly alongside it and deploy your telescope on the asteroid and then have it head out into the solar system. There's no enormous advantage in doing that because, you know, deep space beyond the Earth is dark enough and quiet enough that it doesn't really matter how far away from the Earth you are. So that's not necessarily a primary goal of asteroid work. The primary goal is to show proof of concept that we can deflect an asteroid, which NASA did a few years ago with the DART mission, and then potentially capture asteroid into Earth-Moon orbit for mining or other purposes, closer study. Closer to home than an asteroid in the asteroid belt, the most attractive platform for astronomy in the future, space astronomy, will be the dark side of the moon. Dark side of the moon is, by definition, extraordinarily dark. It's dark as any space environment, but it's a stable geological platform with almost no geological activity to build infrastructure. It's also shielded from the Earth, so there will be no radio interference. So for both radio and optical astronomy, the dark side of the moon would be an extremely attractive place to put observatories of the future.
The next question is from one of our live participants. I'm sorry for the naive question, but is it not strange that more than 80% of all the mass in the universe is so little understood with our current physics understanding?
Well, it's a good question. It's not a naive question, and it's reasonable to ask why in a subject like cosmology, where we have a very clear story for the history of the universe and the Big Bang and then expansion and how gravity forms gas into galaxies and then clusters and gives us the structures we see, to know all of these things and yet not know what the universe is made of seems a little puzzling, but it's the situation we're in. Dark matter was first inferred in the 1950s and 60s, and then was decisively detected by rotation curves or spectroscopy of other galaxies in the 70s and 80s. So we've known about dark matter for half a century, and we still don't know what it is. That's a not very impressive rate of progress, I agree, but dark matter is essentially elusive. It's dark, doesn't interact with light, and that really hinders us understanding what it's made of. It's omnipresent, it's part of every galaxy, it's in the solar system, it's around us as we speak. It's very weakly interacting particles, and that's what makes it elusive. So it's just proving to be a very long research agenda to figure out what dark matter is. And it's going to be big reward, possibly Nobel Prize, for whoever figures it out first.
The next question is from Thomas, who sent an email. Is it possible for the Earth to rotate in opposite directions? Has it ever done so, and what effects would result from a change in the rotation of the Earth?
The Earth has had changes in its rotation rate, but they're subtle. So no, it isn't possible for the angular momentum vector of the Earth to flip, essentially, for the Earth to spin the other way around. The only planet where that seems to have happened was Venus. So Venus is counter-rotating. It's the only planet in the solar system that spins in the opposite direction to its orbit of the Sun. And that is believed to have been caused by a collision very early on. The Earth has always spun in the direction it's spinning, in the same direction it moves around the Sun, but it does have an orbital tilt. And that orbital tilt has changed over time, and the spin rate has changed very subtly due to seismic changes and reconfiguration of the interior of the Earth and subtle interactions with other planets. But there are no wholesale grand changes to the Earth's rotation.
The next question is from Lamar de Cosas, who asks, do you agree with the idea that two galaxies previously collided with our own, creating the initial conditions for the molecular cloud that formed our solar system and accounting for the lithium?
So there are interesting ideas to try and account for the galactic history of the Milky Way. We are essentially certain that the Milky Way formed from smaller pieces. And if we look out and do surveys of star streams, we can see that the galaxy, the Milky Way, is consuming small galaxies and sort of tidally ripping them apart as they fall in. The particular question that's asked is a speculation because doing this kind of galactic archaeology is quite tricky. Once the objects that have combined or merged or collided with the Milky Way are absorbed, their stellar orbits changed substantially, and evidence of their passage and the timing of their passage is very hard to recapture. So I would say there are a number of these speculative ideas to try and explain particular architecture of our region of the Milky Way from collisions and mergers with other galaxies, but none of these is proven beyond a reasonable doubt.
The next question is from one of our live participants. What is the current understanding in modern cosmology about the beginning of the universe? Would it be wrong to say that the Big Bang was the beginning?
No, the Big Bang is presumed to be the beginning. So modern cosmology starts with the Hubble expansion, the recession of all the galaxies relative to the Milky Way, runs time backwards, and then you get a universe smaller, hotter, and denser, and you project back to a singularity, essentially the Big Bang. So that's our best understanding of the origin of the universe. It's bolstered by the expansion that we observe, by the microwave background radiation from the universe when it was very hot and small and dense, and also by the abundance of light elements which were generated when the universe was a few minutes old in the Big Bang itself and not in stars. So those are the three foundational pieces of evidence for the Big Bang, and they're pretty good. So it would be really hard to conceive of a cosmology where the Big Bang did not occur.
All right, the time is now 10:58, so I think we have time for one final question, and then we will be wrapping up for today. Thank you all for joining us. The next question, or the final question for today, is from Terrence, who asks, can planetary orbiters produce their own electricity from the magnetic fields above the atmosphere? And are there any satellites doing this?
Yes, you can definitely. This is classic electromagnetic theory. Goes back to Faraday in the UK, several hundred years ago. So yes, if you move a wire, for example, through a magnetic field, you induce electrical current in it. And so induced electrical currents by motion through magnetic fields is a standard technology. The trouble is the Earth's magnetic field, while globally quite strong, is locally quite weak. So at the level of size of a spacecraft, it's a pretty weak local magnetic field, and so the amount of electricity you can induce is really small. So this has been done. There's been a proof of concept of this. But that amount of power you get from induced electrical energy in a magnetic field is clever because you're getting it for free, is actually much less than you would get just by putting a solar panel on your satellite and just harvesting the sun's energy. So that's still the preferred way of powering satellites, even when they're quite far from the sun. Thanks for all the questions. Good range as always, and thanks to Matthew for facilitating. And I forget our next session if we have it lined up, but usually we have the next few on the calendar.
Yes, that's correct. I think it's a few weeks away. We've got a little bit of a break in here due to some travel. The next one is April 24th, which is, I believe, also a Thursday. So we'll see you all back here, same bat time, same bat channel. And for those of you, I'm not a very good YouTuber apparently, because I always forget to ask everyone to hit the like button on our live session. So for these videos, if you could hit the like button, that helps raise the profile of these videos and helps get them out to more people, which helps our channel. So if you could hit the like and subscribe to our channel, click the bell icon so that you hear about our next live sessions. That would really help us out. So thank you all very much for joining us today, and we will see you all in, I believe it's 3 weeks. Take care, everyone.
Okay, bye.